Okay, so on to the next example. Here we have 0 equals 2x to the fourth minus 4x squared plus 2. Now, just like we previously have done, if we have a common factor, we'd factor it out. And if that was a variable. Here we see we don't have any common factors as variables, but we do have a common factor. But we do have a common factor of 2. So what we're going to do in this case is factor out a 2. So when we factor out a 2 here, we're going to be left with x to the fourth minus 2x squared plus 1. Okay? Now what we notice is the structure of this polynomial is x to the fourth. It's in the trinomial, but it's very similar to like the one that we did up here, where it's x to the fourth, x squared, and then a constant. So what we know then is we just need to factor this and then raise the power of the factors. It's the same type of problem that we have previously done. Now the other problem we have in this example is this 2. What do we do with this 2 here? So, it might be coming to like, oh, well, that means that's a 0, right? But if you use the zero product property and you set this equal to 0, you have 2 is equal to 0. Well, that is not true. That is a, false equation, false statement. So 2 is not equal, so that doesn't even make sense. And so then we got to think about, well, what is exactly 2 doing? If we were to look at the graph, what is that 2 going to do? And if you remember from our transformations of functions, that 2 on the outside, what that did is that was going to be vertically, stretching or compressing the graph, but that's going to be like a dilation, a scalar of the graph. It's not going to actually affect the zeros. So what we can do with this then is actually eliminate that 2. So we can divide by a 2 on both sides. 0 divided by 2 is 0. 2 divided by 2 is 1. So now it's not going to impact our zeros or us solving our zeros. It's still there. It still affects our graph. And if you go and look at the Desmos and graph it, you'll see how it changes, but it's actually not going to be, it's not going to impact our zeros. So if that 2 is there or not, it's not going to, well, actually, that would impact it. No, actually, you'd factor out the 2. If you have this, or if you graph this or graph that, they'll have the same zeros. So you can verify that on your own if you need to. Now, in the exact one, we basically want to see, all right, what two numbers multiply to give me 1, add to give me -2. Again, I notice this is a trinomial, and I notice that this is another perfect square trinomial. So therefore, I can factor this into saying what's x minus 1 times x minus 1. Okay? Now, the other thing that's kind of important about this is, remember, we've got to raise the power of the factors, right? So x squared and x squared. And then, so therefore, we could bring these together, but if you remember in the last example, that wasn't always really the best. We can simplify factor this further. And so we can factor this into x minus 1 times x plus 1. And then we could do it all there, x minus 1 times x minus 1. But what you'll see is you're going to get x minus 1 squared and x plus 1 squared. So if you were to expand these out, again, I'm just reverting back to what I did over here. If you expand them out, you're going to see we're going to have 2 zeros, but they're both repeated. So therefore, what we're going to have is plus or minus 1 are our zeros, and they both have a multiplicity equal to 2. So when you look at that graph, what you'll see is 2 x-intercepts, but they're both going to be bouncing. Okay. All right, so let's do one more trinomial here, and then we'll get on to some new new types of polynomials. So last one again, we see, oh, okay, let's factor that out. That's cool. We have an x squared. Can't factor out between 3, 4, and 1, so I take the x squared. That's going to leave me with a 3x squared minus 4. That's wrong. That should be a cubed. So that's 4x plus 1. Sorry about that. I made a mistake. All right. Now, I had to include one of these because, a lot of times we get pretty good with factoring when a is equal to 1, but then when a is not equal to 1, we pretty much, get stuck a lot of times. So obviously, if you need much more help with this, there's additional resources you're going to want to use. But we obviously know we need to continually factor this down. So let's just focus on this right now. We know that it's a trinomial, so I know that it's going to be, or it can be factored down into a product of 2 binomials. All right. Now, thankfully, it's a quadratic, so we're just going to have, x and x, and we want to see what two terms multiply to give us 3x squared. Well, we could just say 3x and x, right? Doesn't matter if you write x and 3x, just get something. Now we need to know what two numbers multiply to give us 1. So we look at the factors of 1. That's positive 1 and positive 1, and negative 1 and negative 1. And there's really not too much variation. I mean, this is a fairly simple problem because you're either going to do plus 1 and plus 1. Or you're going to do 3x minus 1 and x minus 1. Now, obviously, when you get to problems where there's a lot of different variations, there's other techniques that I teach to help you out with this. But it also gets a lot quicker to really start moving these in your head and trying to see which one of these makes sense. And I can already know which one makes sense because I know my middle term needs to be negative. So if I was to expand this out, I'm just kind of doing some FOIL in my head, I would never get a negative term if I was to expand this out. But when I expand this out in my head, 3x times x is 3x squared, negative 1 times negative 1 is positive 1, 3x times negative 1 is negative 3x, negative 1 times x is negative x, negative 3x, negative x, 4x. Boom, got it done, okay? So I gotta write that back up there. So a lot of this, just really kind of comes into, practice and being comfortable with being able to factor. And so therefore we have x minus 0 squared. Then this was 3x minus 1 times x minus 1. Okay, now what we can do is set these all in, and you can see here is going to be my 0 that has a multiplicity of 2. So I'll have 0 with a multiplicity equal to 2. Now again, if I was to set these both equal to 0, remember using the 0 product property, I would add 1, and then I have to divide by 3. So that's going to give me 1/3, and then this would be 1, and then these both have a multiplicity of 1. Okay? All right, so now we have 4 terms. So we've really practiced a lot what you would expect to see with a trinomial. Perfect square trinomials, factoring out the GCF, and then factoring trinomials to binomials. Right? Now we're going to look into 4 terms, and this is a different technique. So this is going to be the 3rd different type of factoring technique that we are going to explore when finding the real zeros. And same kind of thing. Sometimes it's helpful to factor out common factors if you can, but sometimes it's not always going to be necessary. Or sometimes I think it's a little bit easier actually just to leave them as, as it is, so you can kind of see a little bit more of the patterns. In this example, though, we have nothing we can really factor out. There's no common terms. So what we're going to do is we are just going to what we call the grouping technique. So what I'm going to do is I'm going to group the first 2 terms and the last 2 terms, okay? And again, there's nothing mathematically I did. I am just I'm just grouping the first 2 terms and the last 2 terms. And again, this works when you have them in descending, power form, or you could rearrange them so it works in your own problem. But usually when they're in standard form, that's exactly what you're going to need from there. So now, if I group these 2 terms, what I'm going to do is I'm just going to focus on factoring each grouping set. Okay, so if I look at this, I say, oh, well, they have common factors here, right? I have common factors of an x squared. So what I'll do is I'll factor out an x squared. Now, a lot of students get confused with this because they feel like we're doing something to change the problem, right? And if you notice, when I multiply this back out, I'm going to get the exact same problem. So in here, what I want to do is my idea of factoring out the GCF is to get the exact same terms that are in the parentheses to be the same. So if I factor out a -4, look what happens, what's left over, x minus 1. Okay, so you can see is inside these parentheses, I have x minus 1. Now, it's also really important to understand that these are equivalent equations. Okay, if you multiplied the x squared and multiplied the -4, you would get this exact same problem again. So I'm not changing the problem by any way. All I'm doing is I'm selectively grouping and then factoring out. But I have not mathematically changed the value of the equation or the expression in any way. But now what I can do is I can go a little bit step further. Notice that the x minus 1 and the x minus 1 are common terms. Just like x squared was common in all of these 3, x minus 1 is now common in this term as well as this term, right? Because these terms are subtracted by this subtraction sign. So here's one expression, here's another expression. Within both of those expressions, we have x minus 1 is common. So what that means is I can factor out the x minus 1. So I have x minus 1 times x squared minus 4. Now again, if you still don't like this, multiply this out. You're going to get this expression, okay? You're going to get that expression. So, but now we're in a point where I can now solve this. Now, I probably want to get rid of that squared here and write that as linear factorization. So I just do x minus 2 times x plus 2. And you obviously will know sometimes, just for the sake of time, we can kind of get that quickly. But now we've written everything as linear factorization. We see that we have 3 x-intercepts, and they all have a odd multiplicity. So my zeros is going to be 1, 2, -2. And they all have a multiplicity equal to 1. Okay? All right, so for the next one, you could divide out of 2, and there's nothing wrong with that. I don't know why I'm not going to. I'm just going to. This is just kind of the way that I've always done it, and I see that when I have...
Ms. Lane, you're needed in the principal's conference room. Ms. Lane, you're needed in the principal's conference room.
What I've noticed is just when I see something that has 4 terms, like 1, 2, 3, 4, I just prefer to kind of go about grouping and then factor out terms from there. All right, I don't know. It's just kind of what I'm comfortable with. So again, I'm going to do the same thing. I'm going to group the first 2 terms and group the last 2 terms. Now again, I'm looking into factoring out GCFs. So in this case, you can see that these 2 have a 2x squared in common. So I'll factor out a 2x squared. And I'll be left with an x plus 3. And then here, again, I want to get a x plus 3. So I don't want to factor out a 2. You could factor out a 2, right? But then that's going to leave you with a negative x, minus 3. So that's not going to be the same, right? So if I factor out a negative 2, though, I'll then be left with x plus 3. Okay, and that's what I want. Now, again, you can see that these 2 terms are separated by that subtraction, and they both have an x plus 3 in common. So then what I'm going to do is factor out the x plus 3, and therefore I'll be left with a 2x squared minus 2. Okay, now here is, if you would have factored out the 2, you wouldn't have this common 2 here. So you can see here I can factor out that 2. Now again, that 2 plays an important role, right? Because it doesn't really play an important role. It plays an unimportant role, actually. This becomes an x squared minus 1. But remember, we can divide that 2 out, right? It's not affecting the zeros here. So if I divide that 2 out and rewrite that, I would have 0 equals, and then just write that as the difference of 2 squares, x squared minus, let's write that as x minus 1 times x plus 1. Okay, and now you can write my solution set, which is -3, and let's just write it as plus or minus 1, and they all have a multiplicity of 1. Okay, all have a multiplicity of 1. All the multiplicities adds to your power of 3. Interesting. Okay, so that's basically, that is going to be the summary here. I know there's a lot of different factoring techniques, but you really want to kind of investigate, just to kind of summarize this. When you're looking at 2 terms, look for difference of 2 squares, factor out a GCF. When you look into 3 terms, look for perfect square trinomials, look for factoring out a GCF, and look for factoring into 2 binomials and raising the powers. And when you have 4 terms, look into using grouping. And that's basically kind of about it. Now what we're going to do is we're going to move into, rather than giving an equation and finding the zeros, now we're going to work into what happens when we're given the zeros and the multiplicity, how to write the equation of the polynomial. So that's coming up next.